Okay, let's continue working on reactor sizing. Remember that our focus is to determine the reactor volumes given the rate of reaction as a function of conversion. As you saw before, typically we need to convert, right, the rate as a function of concentration and use some mathematical modifications to get that in terms of conversion. So what happened when the reaction is first order, second order, third order, and when we have differences, right, in the relationship between the conversion of one species and the other. So this part will handle obtaining an expression for different type of reactions. You will be having some final kind of homework assignment after this video, so stay tuned and make sure that you identify where that problem is. Given that the rate of disappearance of A is almost always a function of the concentration of the various species present, then if we only have one reaction occurring in the reactor, each of the concentrations can be expressed as a function of the conversion of X. As we will see soon, right, that we can do those relationships. Therefore, we are going to be using most commonly the rate of disappearance of A as a function of the conversion. Consider the reaction where A is going to products. So as I told you, you have to be very cautious when you define RA as a function of a conversion, because it does depend on the stoichiometry of the reaction. So this is an example. Let's look and consider the following example where we have 1 mole of A going to 2 moles of B, and that reacting, with 2 moles of B, and that is yielding some products. And the statement provides you the rate of reaction. Remember, that should be given to you, or you should be able to get it from the mechanism of the reaction. So let's make us derive an expression for the rate in terms of conversion. If we assume that A is the limiting reactant, we will express the conversion in terms of A. B could be the reactant. If that is the case, it is convenient just to divide everything to get 1 mole of B, and like that get the expression, the conversion expression. So it's just convenience right now that A is the limiting reactant. We will see later that we will be able to determine based on how much you add of both reactants at the beginning and the stoichiometry who is the limiting reactant. But right now I'm just assuming that. If that is the case, I know that that rate law, right, provided experimentally, right, in the statement, equals, right, to the relative rate of A over the stoichiometry equals to minus RB over 2, right? So we can also express this in terms of conversion, right, as say Ca, right, the concentration of A equals to whatever is initially in the reactor or entering into the reactor. We can convert this in terms of flow. We're going to see that later. Okay, Xa. And for Cb, right, the amount of Cb, the concentration of B at the beginning of the reaction minus what is reacting. And if we're defining conversion in terms of A, that means that it's going to be 2 times whatever reacted, right, of Xa. And we can see that here from the stoichiometry of the reaction. So that means that we can move on and substitute these values equal to K, Ca 0 minus Ca 0x, that's the concentration of A, defined in terms of conversion. Cb 0 minus 2 Ca 0 Xa. Okay, I'm just dropping that subscript. We talked about this before. Initial molar ratio equals to Cb0 over Ca0. or rearranging, right, in this case, it will be solving, right, or rearranging the value of m into the equation that we have here, we end up having an expression for the rate of consumption of A just in terms of the conversion of the limiting reactant. Okay, this is the expression that you will be substituting in the in the differential form, right, depending on the reaction we're working. As an assignment, okay, I want you to work this out. This is kind of a homework for you. Let me pause it here for a minute. So now I want you to have fun at home, and you can use the hashtag LoveKimi when you're doing this because you're going to be having fun. I want you to obtain a rate expression as a function of conversion, similar to what I did before, but this time for a given reaction rate for a third order reaction. Remember, this rate can be obtained from the mechanisms or they can be obtained experimentally. So it should be given or you should be able to obtain that theoretically. So have fun with this and be ready for next class trying to solve this type of problem. I want to conclude, right, this introduction to the sizing of the reactor, that you can imagine that the integration or the math becomes more intense as the order and the number of species increase in the rate law. So it is important for us as chemical engineers to define ranges, right, experimental ranges where we can say, well, the order under these conditions probably is, is second order or third order, and we can maybe get some conditions where we have a high conversion and we have a behavior for the reaction to be a first order reaction, which simplifies a lot the analytical solution. Therefore, the solving of the reactor sizing